I'm going to dig into the architecture of SD-WAN. And so if you have any questions, right, please fire away as we go along. I will try to allow some time at the end for some Q&A. And so the first 30 minutes, I'm going to go over architecture and hopefully allow 15 minutes for some actual hands-on and a little bit of a demo of the solution. Okay, so next slide. First thing I want to talk about is platform offerings currently. So y'all know by now that when we acquired Viptela, some hardware came over with the solution. And Cisco, of course, being tooled up for the technologies and platforms we currently have, it just makes more sense to take the existing Viptela hardware and kind of translate that into ISR platforms. So if any of you out there are existing Cisco Viptela customers and you're using the VEdge 100 and the VEdge 1000, they will continue to be supported. But going forward, the new platform of choice is going to be the ISR 1100 4G, the ISR 1100 4G LTE, and the ISR 1100 6G. And the 4G variants are the direct replacement for the VEdge 100, and the 6G is direct replacement for the 1000. All right. Any questions on that from the panel? Okay, or from the users rather. All right. So what those are? That's ISR hardware. It's running VEdge code. The VEdge 2000, the data center box, is not going anywhere. And for any of you who are new to the SD-WAN family, the VEdge 2000 is our data center box that came over with Viptela. It is deployed in more data centers than any other SD-WAN solution on the market, just so you all know. Okay. The ISR 1000 series, the ISR 1121X and the ISR 1161X are new to the 1000 series. One more note on the Viptela OS 1100 4G and 6G. I probably should have mentioned this. With the correctly sized enterprise agreement, the hardware is free. That's right. For every license you buy with the EA right now, and this is a limited time offer, the hardware is free. Okay, I'm going to let that marinate. And they are running VEdge code now, but later on you will be able to change that to iOS XE SD-WAN if you desire, probably sometime this year. Okay, XE SD-WAN, the ISR 1111s up top left, that whole family, and then new is the 1121X and the 1161X, and those support the full stack security feature set, much like the ISR 4Ks. Right? And the 1121X, X has the memory. The X designation means it has the memory. And the 1161X also support pluggable modules for LTE and TDM type interfaces. Then, of course, you have the 4Ks, which is the Swiss Army knife of all routers, and the ASR 1000 for the data center. So for customers thinking about SD-WAN, if you have a current ISR deployment, if you're thinking about an ISR refresh, right, you got 29s or 39s or even 38s out there, and you want to refresh that hardware, that is a really good time to start thinking about the move to SD-WAN. Just want to throw that out there, right? If you have existing ISR 4Ks and you want to leverage that investment, absolutely. 17.2 is going to drop probably next week. When it does, it's going to be a single monolithic code base. This is some cool stuff. You'll be able to run that software, do mode SD-WAN or mode, I think it's autonomous. An autonomous mode, it runs just like a normal or an old school, I'm calling it now, iOS router. Okay, so if you know the story, currently there's two different code trains, and you had to upgrade to a different software to be on SD-WAN, but if you wanted to be on iOS, you have to use a different code version. That's not going to be the case going forward. All right, just so everybody knows. Okay, and then of course you can run it virtualized in VHCloud format in the cloud to support multi-cloud deployments, right? Whether it's infrastructure as a service formally and you want to run the vEdges as VNFs, or if you want to use kind of like an Equinix thing with, say, cross-connect into Azure or AWS using ExpressRoute or something like that, we support those models as well. All right, moving right along. Okay, so we're going to talk about the architecture. It's 11-minute past, so I'm going to move quickly. So what we've done, if you think about the past and traditional routing, right, it was routing by rumor. If you're as old as I am, 55, you probably remember Bassam Halabi's book, Routing Internet Routing Architectures. I think I have revision 2, the BGP Bible, right? It was routing by rumor. The control plane was, I told you, you told the router next to you, and he told the router next to him, and so on and so forth, and that was the control plane. We lobotomized the control plane from the router. We moved it up to the cloud or to an on-premises controller, if you so desire. But anyway, so consuming it from the cloud, let's assume for just a moment, you have the orchestration plane within the control infrastructure, you have the management plane, and you have the control plane. And within the control plane would be what we call the vSmarts. The management plane would be the vManage, and the orchestration plane would be the vBond. And so if you look at this diagram here, it's a one-to-many relationship. And I'll get into that in just a second. But that allows routing updates and things like that to go up once and come down many, which is more efficient than routing by rumor, right? If you think back to the days of BGP dampening. I'm already talking about it like it's past tense. Okay, so orchestration plane, that's the vBond. That does things like recognize NAT types coming from the edge device if it's sitting behind a NATed broadband router, et cetera, so on and so forth. It's also the second place you touch when you bring up a device for the first time and you do a zero trust handshake for the device to get onto the network and be part of the SD-WAN at the control complex. All right, distributes a list of vSmarts and vManage to all the WAN edge devices so that they know who they're talking to. And like I said, it facilitates some NAT stuff. All right, the vSmart, that is the control plane. Facilitates fabric discovery, disseminates control plane information, distributes data plane, and Appleware routing policy, et cetera, so on and so forth. I'll talk about that. Highly resilient. So you get two of each from the cloud. You get a vSmart East and a vSmart West. You get a vBond East and a vBond West. It's hosted in AWS or Azure. You could request either one. So it's highly resilient. Okay, so network-wide control plane. This kind of talks about what I was just saying a moment ago. Remember that 0 times n to the second power control plane complexity, right? When you're trying to figure out the number of OSPF neighbors or BGP peers, and you had that full mesh of peers, and then that facilitated the need for route reflectors, and so on and so forth. If you look to the left, the control plane now lives in the cloud, and the vSmart sort of is like a route reflector. It's just that the control plane logic doesn't exist on the data plane, aka the forwarding plane. I still call it the forwarding plane. Okay, so moving on to the data plane then. That is purely IPsec tunnels and VRFs and the movement of data between vEdge devices or cEdge devices. vEdge is Viptela, cEdge is ISR. All right, so I'm going to move quickly to the next slide. All right, then we have the vManage. That's your single pane of glass. That's where you do all your configurations in the UI. And that subsequently then gets pushed down to the vSmarts and sent out to all of your vEdge or your SD-WAN edge devices. Let's call it that for an all-encompassing terminology. It also facilitates troubleshooting and software upgrades. So a moment to talk about software upgrades. Unlike other solutions, we don't force a software upgrade on you. I was a network engineer. I sat in your shoes for many years on the customer side. And if I walked into work one day and found out that on an enterprise-grade solution that the provider of the solution upgraded the software without telling me, I would have their head on a silver platter. So just let that marinate out there for a second. You have total control, as you might expect from an enterprise solution, of code upgrades. You decide, just like anything else, right? If you don't need a new feature, if it's not broken, you don't fix it. Typically, in the places I used to work, there had to be a very good reason to upgrade code. Maybe it was a maintenance release and there's some bug fix you needed, or there was some feature that you had to have. Those would be reasons for it, but ultimately you control it. That's the point here. All right, programmatic interfaces. So if your shop embraces the DevNet culture and you got people who can code in Python, et cetera, netconf and Yang, RESTful APIs, and there's some things you want to do with the open APIs from the vManage solution, pull down stats, build dashboards, actually push up, using YAML files and such to push things up to the controller. That's all available for you to do. Okay, overlay management protocol. That is the secret sauce. Overlay management protocol is really, under the hood, it's multi-protocol BGP, right? But we don't call it that because using OMP allows us to make changes to it and extensions to it that allows us to be agile and flexible when we bring new features to the solution, right? We don't have to go before any standards boards. So it's TC-based, it's extensible. It runs between the WAN edge routers and all the vSmarts, right? So OMP is where your routing updates come from, your policies, all of that stuff. It advertises control plane and security context to all of the edge devices. So if you think about it then, if I'm applying policies to the vSmart, it's just like before, except now I'm not applying policies to individual edge devices unless it's like a local security policy access list or say an individual routing policy that's unique to that site. Otherwise, it could all be handled with central routing policies. And those are applied to the vSmarts. vSmart in, vSmart out. Remember, direction is important, right? Same thing holds true in this particular situation. Okay, moving right along. So terminology, overlay management protocol, again, OMP, the secret sauce. TLOC, transport locator. A TLOC is simply the point of attachment. It's tunnel endpoint, right? Putting it in terms that you understand from your DMVPN days or your GETS encryption days, right? Listen, I'm talking like it's old school, because it is, it's old school now. All right, so a TLOC basically is where you plug into the network. That's the underlay address, okay? Whether it's a public address, whether it's an MPLS private address, whether it's a DHCP address from a broadband provider, that's the underlay address. A VPN is a device-level network segmentation. And if you're old school like me, right, your mind automatically takes the word VPN and it associates it with an IPsec VPN. But really, think about it more like MPLS segmentation, because that's what it actually is under the hood. It's a VRF. Okay, so OMP routes advertised, two major route types, OMP routes and TLOC. A TLOC is next hop layer reachability, right? So a TLOC route, that's the prefix at the site. And if it shows the TLOC IP as the next hop, that's how I get to that prefix. And you'll see those in OMP routes. I'll try and show those to you. Okay, let's move right along. So this is probably my favorite slide when I demonstrate the solution or talk about the solution with customers, is how the tunnels are established. So first thing, we establish a DTLS and TLS tunnel using a zero trust handshake. Once that is done, there's some things that happen after that. First thing that happens is I advertise my TLOCs and all the attributes of the TLOCs to the vSmart, and then the vSmart showers that information down to all of the edge devices. Each device does the exact same thing. Well, once all parties know about all of the available TLOCs, in other words, if I see route updates come from the vSmart and I see a next hop as a TLOC, I want to build a tunnel there if policy permits me to do that so that I could establish reachability. So what do I need? I need your updates to come down to me from the vSmart. And boom, once that happens, IPsec tunnel comes up. BFD, bidirectional forwarding, keeps the tunnels up. We use BFD. Doesn't stand for big freaking deal. If you're from New York, it does, like me. I'm from Long Island originally. Bidirectional forwarding detection keeps liveness detection, but it also polls for latency loss and jitter. We'll talk about that in just a minute. Okay. Look at that. I didn't lie. Just a minute. Bidirectional forwarding detection, path liveness, and quality measurement detection. So we use BFD in echo mode. I think the packet size, I want to say it's 179 bytes. It's a small packet. So with liveness detection, it's highly tunable. It's not WYSIWYG. Also with latency loss and jitter for application-aware routing policies, it's also tunable. It's not WYSIWYG. One of the favorite demonstrations that I have with my customers, I'll take a layer 2 switch, I'll put the layer 2 switch in front of the edge routing device, and then I'll cable through, and then I'll cable on the opposite side of the switch to the broadband router, let's say, when I do the demo. And I'll pull the plug out, the Cat5, on the side facing the modem. Why? Because I don't want line protocol to drop on the SD-WAN router. Why? Because if line protocol drops, well, that's an easy demo. Any vendor can do that. It's simply a routing decision. So how do we make it more impactful? Well, if I want to show you that BFD liveness detection is really working end-to-end across the entire path, I'm going to pull the cable out so I don't lose line protocol. And then you get to see how highly tunable BFD is, and you get to see how well it works when it instantly fails over to the next path. I didn't say link, I said path, because we're talking end-to-end. We're talking between all edge devices, if that makes sense. So if you look at this graphic here, if I have a full mesh topology, let's say all sites can talk to all sites, I want BFD liveness detection across all paths. And so that kind of takes that whole, well, what's going on underneath at the transport layer? It doesn't matter, right? SD-WAN is like the honey badger. Honey badger don't care. And so at the end of the day, if I want to have multi-transport capability or transport independence, right? If I want to have, let's say, MPLS from one carrier and direct internet from another, and I want to leverage broadband or LTE, and I can build a unified fabric over all of them, and then use BFD measurements for application-aware routing and liveness detection, I have true transport independence. That's what this brings to the table. Okay, so route distribution. So you've probably heard a lot of talk how we support BGP, OSPF, enhanced IGRP. I'm old school, it's enhanced IGRP. I remember IGRP. Okay, anyway, we will take that from a service-side VPN. I'll show you what a service-side VPN is in a second. We'll redistribute that routing information into OMP. From there, it goes up to the vSmart, as you might have guessed, and that information gets distributed down via OMP. OMP updates instantly to all of the edge devices so that reachability is established. So that if at your data center, for example, you're doing a project and you add a new prefix at the data center, and if you're like me and you love BGP, and you're redistributing from your data center routing protocol into eBGP and then into OMP so that you could do things like meds and make your failover predictable and have, say, one vEdge device be the main vEdge device and at the data center and the second one be the secondary device. You can use things like BGP meds, you can redistribute, and you can have predictable routing updates so that if you're adding a prefix at the data center and it gets redistributed, it automatically gets redistributed very quickly up to OMP and down, and reachability is established instantly to all of your edge devices. Okay. I'm going to stop here for just a second to look at the Q&A. Panelists, are there any questions that I need to answer? Because I can't see them. For some reason, I can't see the questions.
No, we're good.
Okay, awesome. Zero-touch provisioning. So, Joe, yes, I want to put these SD-WAN devices into my network, but I'm afraid. How do you do this? Well, we do this thing called zero-touch provisioning. Burnt-in TP chip on the device has CERT burnt into it, and it does the zero-touch provisioning handshake. Your first stop is ztp.viptela.com. The ZTP service says, hey, you belong to this organization over here because it knows your serial number. Because you bought the solution, you got an enterprise agreement, all of the serial numbers were pre-populated in the back end, and so the database knows about you and says, oh yeah, you need to go over here and talk to this VBON. The VBON says, I'm not talking to you until you establish a zero trust handshake. You do the zero trust handshake, and then the VBON says, okay, we can have a conversation now over TLS or DTLS. It's highly secure. The VBON says, oh yeah, here's your vSmart, here's your vEdge, go talk to these guys. And then the vSmart says, I don't know who you are, and it does the zero trust handshake again. And the whole thing happens very quickly, and the control plane comes up, and then you're allowed to talk. Okay, moving right along. We talked about VPNs before, and I mentioned server-side VPN and exchanging routes. You can have up to 62 service-side VRFs for segmentation purposes. That number is going to increase very shortly. I can't say when. It could be March, it could be July, but that number is going to increase very shortly. Although, if you have a need for more than 62 VRFs, I want to talk to you. I want you to be my customer. But you're probably in the banking industry, right? If you have that many VRFs, or even the medical vertical, or possibly law enforcement. Okay, so 62 VRFs on the customer side. It's true segmentation across the WAN. And what we do is we give you a VPN 0 for the transport side. And the only thing VPN 0 cares about is TLOC interfaces and knowing how to get to other TLOC interfaces so that we can build tunnels. We try not to do internal service-side prefix routing over VPN 0. That's for all of your service-side VPNs, right? And then you have VPN 512 for in-band, out-of-band management, if that makes sense. Okay, so another way to view that, if this makes sense, right? Let's say you had MPLS and Internet. That's in your transport VPN, aka VPN 0. Your site networks, whether it's your data center or your remote site, those are your service-side VPNs. And how do we do that? I said earlier, MPLS tagging. It's exactly what we're doing, only you're not configuring LSPs by hand. You're not configuring layer 3 VPN BIS by hand. That's all done with a few clicks. And under the hood, we're introducing basically MPLS tagging or multiplexing multiple VRFs over a single IPsec tunnel. That's how we secure it, right? So if you wanted true segmentation on the LAN side, if you had multiple .1Q VLANs, you could map those to VPNs, segment that all the way across the wire in this fashion, and then on the data center side, have multiple .1Q VLANs that map to different firewall interfaces on the data center side. That is true end-to-end segmentation. So unlike some of our competitors who will tell you, oh yeah, we do segmentation, and it's just a bunch of firewall rules, that's not really segmentation across the WAN. You want to separate that traffic completely in total isolation. We give you the ability to do that. And that also provides you the ability for arbitrary topologies. So how cool is this? I could have VPN 1, let's say, although I probably wouldn't use VPN 1 because if you're a Cisco shop and you have VLAN 1, right, default VLAN. But let's say you had VPN 2, VPN 3, VPN 4, and you wanted VPN 2 to be hub and spoke. But then VPN 3, you want it to be a partial mesh. Maybe you have a call manager and you have those call managers placed in different strategic locations in like regional hubs. And so you wanted all that call control traffic to go over specific partial mesh topology or be service chain or service insertion. We support that all over the same IPsec tunnel infrastructure, if that makes sense. And then you can do full mesh or point-to-point for very specific use cases, all centrally controlled with a few clicks via central policy push from the vManage through your vSmarts and down to all of your edge devices. Okay, so talking about large global scalable enterprises, again, I'm going to say something to you. SD-WAN is not a feature, it's not a chip, it's an architecture. Let this slide sink in. It's an architecture. If I had multiple Americas, Asia Pac, EMA, and I wanted to have, let's say I had thousands of sites or hundreds of sites in the Americas and in Asia and in Europe, and I needed a scalable solution for hundreds to thousands of sites, this is it. This is your architecture. It's SD-WAN. Being able to push routing updates down to all different sites and have them to be able to connect to each other over a high-speed fabric, that's an architecture. being able to provide the segmentation I just described to you. That's an architecture. Here's another view of, let's say, the same thing. We actually have customers doing this sort of architecture too, where they have a high-speed backbone, let's say, using dark fiber or Equinix data centers, where they interconnect all of their hub sites together, do like a high-speed backend, almost like in like a carrier network, and then using SD-WAN as the fabric, facing the edge devices. Again, there's a lot of ways we could skin the architecture cat, right? You want a solution that caters to architecture and brings all of the wonders of SD-WAN through a centralized UI. It's 1:31. I do want to allow time for me to show you what the UI looks like. So I'm going to quickly go through some possibilities for connectivity, and then I'm going to show you what the UI looks like. So transport connectivity, right? MPLS, Internet, VPN 0, as I mentioned earlier, and then your site VPN. Kind of basic. BFD is what we use to direct or to detect liveness across the wire, and also for application-aware routing, which I mentioned earlier. A little note on application-aware routing. Application-aware routing gives you the ability to measure latency loss and jitter across all of your transports, right? And then utilize that measurement to build SLA policies. So let's say you build an SLA policy that says latency, and no more than 250 milliseconds of latency, no more than 10% jitter, or 10 milliseconds of jitter rather, and 2% packet loss. With that SLA as a measurement now, I'm going to build a policy, a central policy that matches on, say, DPI, where I can match applications based on application recognition, or I can match based on DSCP markings, I can match based on source destination prefix, et cetera, so on and so forth. Once I have that match condition, I say, okay, if this SLA has been violated, take that application group, right? Because now I'm matching, let's say a match based on your VoIP, based on critical applications that can't tolerate more than 250 milliseconds of latency, the SLA I just described. I put 2, 3, 4 applications into that application group, and if that SLA is violated, I could pull just that application off the path that's experiencing the SLA violation, yet keep using all of my other paths with that transport independence I talked about earlier. So if you've got applications that are more tolerant to that specific SLA requirement that I mentioned earlier, they can continue to use the path that violated the SLA for the more sensitive apps, yet the more sensitive apps will get pulled off of that path and only go on the other paths that aren't currently violating that SLA, and then come back onto that path when it's in conformance with the SLA. That's application-aware routing. Okay, needed to make sure I told you about that. So we talk about transporting connectivity. We could support complete CE router replacement out at the branch, or even at the data center. Although a lot of customers choose to keep dedicated CE routers at the data center. I'll show you why in a second. But we support complete CE router replacement with direct internet access at the branch so that you don't have to go all the way back to the data center. What we used to call back in the day split tunneling, right? Okay. The only thing you need is a default route basically to the PE router. You don't really have to run BGP, although advertising the /30 between you and the PE router is probably necessary in some instances. But you can see here that we support multiple ways to implement that, right? So with the CE router in place, the CE router can advertise that /30 between you and it. You could even connect up through a LAN core switch. There's a lot of ways to skin this cat. Most customers at the branch choose to do the example to the far left for economies of scale, because it just makes sense. I have the ISR 4000, I want to replace it, so the one all the way to the left makes the most sense. In some instances, though, you may have some supported feature on an ISR 4K that is not currently supported on the SD-WAN platform, and so you stick the SD-WAN router behind your ISR temporarily. And then you upgrade the ISR later on, possibly. Okay. Internet transport integration. If you want to stick a firewall in front of us, you want to stick the firewall behind us, it really doesn't matter. If you want to run the firewall capability on the SD-WAN router, it doesn't matter. You could do that too. Point of this particular slide is that they're all supported. Okay. So let's say I want to have redundancy, but as we all know, carriers charge us for an extra /30 routed link from the PE router to you. So how could I leverage high availability? We do something called the TLOC extension that allows you to leverage the connection that is on the other router as though it was physically connected to you. It's not a protocol. It's not an active-passive thing. It's each edge router gets to use the transport of the other router in an active-active fashion. And then if router 1 fails for any reason, I still have the transport on router 2, right? And router 2 keeps the site alive. Or if an interface dies on, say, router 1 on the left, and I can't get to the transport over there, I can continue to use the transport off of router B, right? So in the absence of full mesh on the northbound side, because it's too expensive, and maybe this site, it's a corporate site, but it doesn't have the importance level that dictates you getting an extra /30 routed link, you could do what we call a TLOC extension here. Okay, site redundancy, we support that. Obviously, VRRP on the layer 2 side, facing the hosts, we support that capability. At the data center, I definitely wanted to talk about that. Integration at the data center. So we love to use BGP where possible. And what I try to do when I do a proof of value with my customers is to be as unobtrusive in the implementation as possible. And so on the northbound side, notice what we've done here. We keep your CE routers in place. And simply, the CE routers need to just advertise the /30 between us and, hold on a second. Sorry about that. That was my personal landline. Okay. On the CE routers, just like at the branch, the only thing you need to do is advertise the /30 that connects to the SD-WAN routers indicated here in blue out to the underlay so that the TLOC interfaces know how to get to each other so that they could establish IPsec tunnels. All the routing from prefix to prefix then is handled in the overlay, giving you that transport independence, okay? If we need to get to the internet to the firewall, not a big deal. And then on the LAN side then, we facilitate routing with a dynamic routing protocol, let's say BGP, which is my favorite, and we'll redistribute those data center routes into the SD-WAN. So what does that allow you to do? In a hybrid situation where you have sites that are on the SD-WAN that haven't been migrated yet, that allows you to hairpin to the data center so that we advertise SD-WAN prefixes through the overlay. The overlay then, here in the data center, redistributes those back into the data center so that we have reachability to all the branches that are on the SD-WAN, and likewise, the branches that are not on the SD-WAN know how to get via OMP, as I mentioned earlier, to the sites that are not on the SD-WAN through the data center. Yes, we're talking about hairpinning, back out to those sites that aren't on the SD-WAN. All right? Later on, once you've migrated all your sites, you can choose to have the SD-WAN routers become your MPLS CE routers. We support that. Okay, moving right along. So other ways to integrate in the data center, right? We could do this. We can have .1Q tagging take place here, and I could have the LAN side and the WAN side, the northbound, the VPN 0 side, and the server-side VPN all connect to the same physical interface, because as we're doing the proof of value, maybe you don't have enough ports left on your data center switches, or you don't, at the branch potentially, you don't want to swap out your CE router because you just don't trust the solution yet, whatever. This can support leaving the CE router in place if you don't have enough ports using .1Q tagging, right? Or you could do this, right? And leverage extra ports on the CE router and let natural routing handle the northbound side, right? And so you're going to send the encrypted packets to the CE router, and then the unencrypted traffic goes to the LAN side, and use a dynamic routing protocol. Okay. Make sense? All right, we're going to move along here. We have, it's 1:41. Give me a second. I'm just going to run through some of the additional slides. There was 2 more I did want to show you that speaks to what I call overlay and underlay routing. Gives you a good visual, and I'm going to actually show you what the CLI and what the templates look like and what the UI looks like. Okay, let's go to this one here. All right, so from the branch perspective, right, so in this diagram, I have one router that's not on the SD-WAN yet, that's in branch 1, and then branch 2 and 3, they are on the SD-WAN. So how might communication take place? So I'm going to go to the data center if branch 1, this is the preferred way, by the way. Overlay and underlay routing and using route leaking can produce routing loops, as you all know. It's not my favorite way to do things, but we can support it. We can throw up filters. Voice can withstand up to 300 milliseconds of latency, so hairpinning through the data center is generally not a problem. Right. And so having said that, traffic is going to hairpin through the data centers. You can see branch 3 here. If branch 3 and branch 1 need to communicate, it would look like this. The green being the IPsec tunnel, right? If you lose a link, we're going to continue to go through the data center. All right. If you're on the SD-WAN, obviously, if your policy allows spoke-to-spoke communications, it would look like this. All makes sense. Okay. I wanted to make sure we talked about that. Let's see, is this slide relevant to the conversation? Yes. So I mentioned earlier, we can allow site-to-site communication via the underlay, and in this diagram, you would keep your old CE router to facilitate that. Okay, that's another way to skin this cat if you didn't want to go to the data center. Hey, you remember I said earlier it's an architecture? Let this picture speak 1,000 words. SD-WAN is an architecture. There's a lot of complexities and a lot of customer environments that just can't be facilitated by other vendor solutions because they don't allow for the enterprise-grade policy controls and routing architectures. That's really, I don't know how else to put that. Okay, going to look through here to see if there's any other slides I wanted to show you that talk to this, and I don't see any. So with that, I'm going to jump to, yeah, sorry, that's me on the drums. I have a 9-piece band, which I also manage. And it's like herding cats. All right, let me share out something else. Okay, this is the UI, and this is our demo rig. So I wanted to kind of show you that what I said before about routing and what routing looks like is for real. But before I do that, this is the CLI from a vEdge router. I'm going to log in here. This is from my lab. I don't have the lab spun up because it's way too noisy, so you're not going to see anything in the routing table. But I wanted to show you from a policy perspective and from a configuration perspective what the CLI gets when you push down configurations from the UI. It's actually pushing a configuration out to the device, right? And it's broken down into different elements. You can see here we talked about BFD earlier, and we talked about that interval being configurable and highly configurable in terms of your different SLAs, and it certainly is. We also talked about, so this here, if you look here, where it says color public, color biz internet, this is for your liveness detection, and then down here, this is specific to your app route, okay? And what that detection looks like in terms of multiplier and how often the BFD pings go across the wire. We talked about OMP. There's your configuration. We talked about VPN 0. There's your configuration for VPN 0. We talked about interfaces getting placed in VPNs. There's your interfaces. We talked about service-side VPNs. There they are. And here's my route in VPN 0. It's a static route to tell my TLOC encrypted traffic how to get to the next hop so that I could get my TLOC interface traffic out to the underlay so that the overlay can handle all of the OMP routing. Right? So that's basically what short version of what CLI looks like on an SD-WAN router running vEdge code. Okay, from the UI then. So if I go here to monitor, I go to networks. These are all of the devices in this particular overlay that are managed by, or within this organization. That's a better way to look at it. And so if I drop down into a particular data center router, and I wanted to see from its device level perspective, I wanted to see some things in real time, I can do that from the UI. This also is available to you basically from the CLI as well. So if I wanted to do show IP route, I could drop to the CLI to do it. Or if I wanted to do it from the UI, it's also available for me to do it here from the UI. The UI in some cases is a little better because from a tabulation perspective, it organizes it into a more concise view. But you can see here, these are all of my routes. And how are they learned? So these are installed in the local IP routing table, right? But they will learn via protocol OMP before they got put into my local routing table. I could see what my next hop is, whether it's IPv4 direct or whether it's learned via a TLOC interface remotely. I can see that all here in OMP. And it's much like BGP, as I mentioned earlier. I could see my BGP neighbors. I could also see my OMP peers. So if I take a look on a router and I do show OMP peer, I'm only going to see the vSmarts. Why? Because I'm only peering with the vSmarts. Remember we said the control plane was moved to the cloud? Now if I jump on a vSmart and I do a show OMP peer, I will see all of the edge devices and all of my vSmart devices. So if I go here to a vSmart and I want to look at OMP peers, I see all of the gateways and I see all of my fellow vSmarts. See here, there's a vSmart, but also all of the vEdge devices. So that kind of typifies that one-to-many relationship we talked about earlier. And here on the vSmart, if I want to see OMP advertised routes I'm pushing down to all of the edge devices before the device actually installs it in its local routing table, I can see all of the edge, all of the OMP routes that I'm pushing down. There's a lot of tags here. You see the TLOC IP that learn the route. You see which peer I'm sending it to. You can see the encapsulation for that particular TLOC, whether it's IPsec or GRE, how it was learned, protocol connected or over protocol eBGP. That also means, and you can see different labels, that also means that you have a lot of match criteria for your policies. If you're writing policies, there's different ways you can match to enforce policy for hub and spoke, full mesh, partial mesh. Right? There's different ways you can match to have custom control policies. If I want to have control over, let's say I had two data centers and I had a default route in both data centers, and I only wanted the default route in data center A to be primary for all of the sites on the West Coast, and the default route from data center B to be primary for all of the sites on the East Coast. I could use that matching criteria that I just described to you in what I call a custom control policy, and I can match and then use site IDs and site lists to send that particular prefix as primary out to the sites that are closest to it geographically, but then as a backup to the sites that aren't close to it geographically, and vice versa, and have data center diversity for the default prefix, but also for more specific prefixes. I could do the same thing. Remember when I said it was an architecture? Yeah, let that kind of marinate there for a while. And then you have full visibility within the UI to see other things like the system status, to do some troubleshooting. It's grayed out because I'm on the demo rig. I can't show it to you, unfortunately. But you have different ways to troubleshoot. Actually, I think I have a live vManage here that doesn't yet have any edge devices connected to it. However, if I go to network and I go to vManage, or vSmart rather, and I wanted to do some troubleshooting, I could do ping and trace route. If it was an edge device that had tunnels up, I could actually show you what the flows look like from that particular edge device's point of view over the particular VPN tunnels. A full-featured solution. I showed you a lot. I went a little over on my slide deck. Apologize for that. But I wanted you to have a little bit of a taste of the CLI and what things are available to you in this architecture. If you haven't seen the vManage, what the UI looks like on, say, your landing page, here it is. Here's actually probably a better view from our demo rig of the main dashboard. You can see I have full visibility into all the applications that are being visualized through the solution. I could drill down onto those to see individual conversations. Okay, who's talking? I also get a look holistically of latency, loss, and jitter from all of my tunnels. It gives me a look at what's going on historically over the different carrier networks. Okay, so I'm going to stop there, and I'm going to ask the panelists, are there any questions from the viewing audience?
No, Joe, someone did the slides and gave your Cisco email as a way to with you.
Okay, awesome. All right, folks, I'm going to give you back some time. If you don't have any questions in the chat, if you do have questions, put them in the chat room, please. If you have questions afterwards, get with your local SE. Make sure if they are SD-WAN specific questions that you ask for the Viptela TSA, Technical Solution Architect, to be present that supports that account SE. We work as overlays to the local account teams. I support the Southeast region of the United States for what we call the commercial select. So I support Florida, I support Tennessee, I support Georgia, and I support the Carolinas. So if you happen to be one of my customers, certainly you could reach out to me directly. My email is jorubino@cisco.com, jorubino@cisco.com. And if you fall in that Southeast Select operation, I could be your TSA. And if you want to have a conversation, we could have a conversation. And if I'm not your TSA, if you are in the territory, commercial territory, let's say, or part of enterprise, I will certainly point you to your correct team. With that, I'm going to stop sharing if there's no other questions. I thank you for your time. I thank you for joining. I really hope this was informative for you. And have a great day.
Thank you, Joe, for a great presentation and the demo. And thank you to our audience members for your time and participation today. Thank you so much, and that does conclude our presentation today.